My name is Jacob Clark, and I'll be doing the Acoustics Finite Element Method Overview. I'm part of a finite element group with Robert Ellers, Josh Ruada, and James Wong, and my part of the story is the theory. So for today's agenda, I'm going to go over what is acoustics, how does it apply in mechanical engineering, then going into the finite element methods in acoustics, acoustic harmonics, acoustic modal analysis, vibroacoustics analysis, segue into ANSYS simulation, and at the very end of this, at the very end of this PowerPoint, there are some resources available if you want to take a look at them. What is acoustics? Acoustics is a branch of physics that studies sound. Sound is vibration, and just like with any vibration, there's an amplitude and a frequency. In the case of sound, a higher amplitude means a louder sound and a more violent vibration, and in terms of pitch, a higher pitch means a higher frequency. And in the case of what we are studying mechanical engineering. So how does it apply to mechanical engineering? Acoustics engineering is a branch of mechanical engineering devoted to acoustics, which is the design, control, and analysis of sound. Now going into this, there are many different applications of this field, including designing amphitheaters, controlling the sound of the exhaust through the muffler, and of course, making sure that structures and systems actually meet acoustic standard requirements. So for the first step, we're going to go into how this all boils down in finite element methods. So finite element methods enable computers to conduct complex acoustic analysis of systems that normally wouldn't be possible by hand. And in the scope of this, we'll be doing acoustic harmonics, acoustic modal analysis, and vibroacoustics analysis. So to start off with, we have to do the basic fundamental equation that everything's going to be based off of. So this is the second order Helmholtz equation for steady state acoustic pressure, P, in a bounded fluid domain, V, which is the volume of the fluid, enclosed by boundary surface omega due to time harmonic external surface distribution, Q. K is the acoustic wave number omega over C, where C is the speed of sound. So just starting off with, you can kind of see how we have the gas enclosed by the volume, and because of that volume, sound will propagate within the fluid. Now, rho omega is the density of the fluid, and QXYZ is sort of like an excitation, almost like a forcing term. So acoustic harmonics deals with with analysis of noise propagation inside a system. So this is the sound change from the entry to the exit of the exhaust pipe. This is, power loss or transmission loss through the system. And this is mostly dealing with just the fluid medium itself. So the Helmholtz equation will be used to convert to a finite equation. First step is using the weighted residual method to convert it into an integral, as we see below. As you can see, the integral looks very similar to the Helmholtz equation, and so from this integral, we use the divergence theorem and substitute it into the original equation. You get this weighted equation. So as you can see in the weighted equation, there are different terms. There's like a stiffness term, a mass term, a term associated with the fluid boundary, and a term associated with the fluid volume. The fluid domain V is discretized then into finite elements VE with nodes defined at each element. The pressure P is approximated below. So you see P of XYZ turns into P hat. P hat turns into the number of elements associated with X, Y, and Z. And when you add them all together, you get back to the original whole pressure system. So the pressure gradient is approximated by applying element shape functions to the finite discretizations. So you turn that gradient into a series of differential, partial differential, and then from those partial differentials you can get the shape function and get matrix B, which you'll see later. The element stiffness matrix of an uncoupled system is as follows. So you take that original term that was in the original equation, you apply you break it down into the elements and you get that formula. Same thing goes with the element mass matrix. You'll see here the 1 over c squared is sort of very similar to inertia, and that's sort of what that term is. It's like the inertia of the fluid in terms of vibrations. And then source excitation vector Qi, as you can see, still has the same original constant, but also has this additional factor here, direct delta function, due to it being discretized. The input velocity vector, so what this is what happens when you have a value for the velocity of the fluid entering the system or exiting the system, and this is the contribution of that to the forcing term. And the input pressure vector, Pi, that is similar. Instead of input velocity, though, there's input pressure. And when you have input pressure and input velocity and the Qi, those are all your forcing terms. So like in the case of our class, we have K, D equals F. Instead, this is K, M, and C times P equals F. So acoustic damping matrix, this is the last term we're going to need. This is the matrix of the damping of the acoustic system. So when you actually plug it all in together, you'll notice that on the left side of the equation it looks very similar to a second order spring equation. You have a damping value, you have a mass value, you have a K on one side with Pi as your displacement. Notice how pressure is like our displacement. And on the other side you have Q, V, and P, and those all relate to the forcing terms that get added on later. The global equation is then solved by directly applying a range of frequencies. So just like how we worked it before, once we generate that global stiffness matrix, you solve it just like we did before. The only thing that gets weird is that since we have a frequency value, omega, that's a value that we just kind of put in. And when you apply a range of omegas, you get to see how the system will interact with sound waves propagating at a different frequency. Now, in order to gather important frequencies, frequencies that are critical to the system, modal analysis approach is needed instead. So the modal analysis identifies key frequencies in the system that will cause sharp increases in noise generation. Mode shapes are obtained with the eigenvalue problem, Ka phi m equals omega m squared ma phi m. So as you see, phi m is the eigenvector. Nodal degrees of freedom are expressed in terms of modal vectors instead of the typical. So Pi turns into phi times phi m. And plug it into the acoustic FEA model, you get the modal model below, which looks very similar, but everything's in a different domain. So modal mass, stiffness, and damping matrices become as follows. K turns into phi, K phi, Ma turns into phi, Ma phi, Ca turns into phi, Ca phi. From this, the mass, stiffness, and damping matrices become Ma equals identity, Ka becomes omega squareds. Those are like relating to your eigenvalues that are important. And Ca turns into 2 times the damping constant times omega, and the damping coefficient's on the right there. The final model to solve is P of x, y, and z approximately equals the shape function times Pi, which equals the shape function times phi m. Now, vibral acoustics analysis, this is important in that if you want to model a system where you have an acoustic fluid interacting with a structural boundary. So this requires both the structural FEA model and an acoustic FEA model. The structural and acoustic models are shown in further slides. There are 3 approaches to this, either Eulerian, the Lagrangian, and the mixed approach. Most finite element softwares use the Eulerian method mainly because it is the most accurate, but it's definitely one of the harder methods mathematically to derive. So the Eulerian method, the acoustic response is typically described by a single scalar value, in this case pressure, while structural response is typically described by a single scalar value for displacement. Just like in our class, displacement is key in structures. So the acoustic FE model, same as before, and the resulting model when you apply constrained degree of freedom is Ka plus j omega Ca minus omega squared Ma times Pi equals Fa. Notice the subscript A. That's going to be important later because that's the acoustic part of the system. The structural FE model, as you see, there's W hat X, W hat Y, W hat Z. What that is that's just a displacement in X, displacement in Y, displacement in Z. And NS and NW are shape functions. So the resulting FE model with unconstrained degree of freedom is Ks plus j omega Cs minus omega squared Ms times Wi equals Fs. So this is like the element model. And you notice again, S is the subscript for structure. The next step is coupling both models together. The first step is to include pressure in the Fe model. So you're going to have the same initial terms on the left, the Ks, Cs, Ms, but you're also going to add Kc Pi. So what that is that's the contribution of the acoustic system to the structural system. And then Fsi. So notice that there's a slightly different F, and that's because you're going to see later what that is. A coupling matrix Kc becomes the sum equals 1 to NSE of the shape functions relating to both the structure and the acoustic system applied across d omega, omega being the boundary between the two. The excitation vector thus becomes Fsi equals Fs. Fs is basically like the forces in the structure that were already there before the contribution of the acoustic system. And then you see the contribution of the acoustic system. You have the boundary side, you have the summation of all the different shape functions multiplied together, such that the only things that really are applying to the structure is that boundary between the acoustic layer. That's what makes sense. So then, going into the acoustic model, you have to add the shell displacement approximation. So again, just like before, on the left side of the equation, it looks very similar. You have Ka, j omega, Ca minus omega squared, Ma, Pi. Notice how Pi, not Wi. But then you have minus omega squared, Mc, Wi. Mc is the coupling matrix between the two, and Wi is the displacement along that boundary of the acoustic system, equals Fai. So the coupling matrix MC, as you notice, looks very, very similar to Kc. The only difference is you see a rho naught there, and that rho naught again is the density of the fluid medium, and it's applied again at the boundary between the fluid and the structure. The excitation vector for the acoustic portion thus becomes Fai equals Fa, which Fa is the forces, like the harmonic forces that we've solved for before. Fa is just what was already there before you have the structural side adding in. And just like with the structural side, you have this added factor where you have rho naught omega squared times the multiplication between the shape functions between Na and Nw. So that's what's basically bounded between the structure and the acoustic system. So comparing the coupling matrices, you'll notice that MC equals minus rho naught Kc transpose. The resulting Fe model then for an interior coupled vibroacoustic system is Ks Kc 0 Ka plus j omega Cs 0 0 Ca minus omega squared Ms 0 rho naught Kc transpose Ma times Wi over Pi equals Fsi over Fai. Now, just interpreting this, you'll notice right away that these matrices are not symmetrical, and that's important to note because the reason for that lack of symmetry is that you have an acoustic system applying directly to a structural system. So it's not just one element anymore. It's two different systems interacting with each other that's going to cause this. And then another thing of note is that in order for this to reduce the computational needs of this system, you have to make sure that you have the same nodes and elements in the structural system as the acoustic system. Otherwise, you're going to add some geometric fudge factors in at the very end. So this is where we segue into the ANSYS simulation. And as you know, my group has been working on a exhaust system simulation, and members of our group are going to go over, first off, how to run ANSYS and how to import the model and everything, and then also what kind of data we're going to pull out from it. Thank you very much for your time.
For this portion of the video, we will go over how to model the muffler of a car exhaust system in ANSYS. We will be modeling from the exhaust engine side of the exhaust port to the atmosphere side. The first thing you need to do is understand the model you're working with. And to do that, you'll have to understand what the inside of a muffler looks like. Mufflers are generally filled with some sort of baffling or resonance chambers or perforated pipes with the intent to destructively interfere sound waves to reduce the decibels from the input side to the output side to help silence car engines from creating too much disruptive noise. So first we created our model in SolidWorks, and the important part here is this model is not the steel case of the muffler. It is actually a model of the internal volume of the muffler. So this solid model represents all the air within the muffler from the input side to the output side. You'll see we have a number of resonance chambers as well as perforated pipes to help reduce the decibel from one end compared to the other. So I took this file that I made in SolidWorks and I saved it as a step file to use in ANSYS. So to get ANSYS started, you'll need to launch the workbench. The workbench is where you'll be able to see all of your different analysis options and also set up your project workflow. Okay, so this is the main home screen of the ANSYS workbench. And from here you can see that our acoustic analysis options are harmonic acoustics, modal acoustics, and static acoustics. For this example in particular, we'll be doing harmonic acoustics, though the difference between these three was explained in the previous section of our video in theory. So either double click or click and drag the analysis that you want to your project schematic page. And once that's loaded in, you'll see the 7 different subsections that you'll need to either complete or edit values in order to complete your analysis. First section is just the type of analysis. As you know, we chose to do harmonic acoustics. The second one is engineering data. Engineering data, you'll notice, already has a green check mark because it comes pre-populated by ANSYS. If you double click, it'll open up what's in this section, and you'll notice that it is the material properties for any of the parts you'll be using inside of your analysis. In our case, we're just going to stick with air, though if we were doing a static acoustics analysis, you might also want to add in structural steel for enclosures of the casing, but we'll just be using the default values for the purpose of this presentation. So close that out to get back to the project schematic. Next, we'll need to do the geometry. This would be that same step file that we had used earlier. You have a couple options. You can either create your model within ANSYS's Space Client or Design Modeler options, but I prefer to use SolidWorks in this case, so I'm going to import that step file that I created earlier. Just go ahead and browse, choose the one you want, click open. You'll notice down here it's in the Files tab. If you don't see that, you can highlight what tool tips you want to have appear at the bottom. And this has the same path. So if you're sharing ANSYS files, another important part is to make sure that you update this path. If somebody sent you a zip folder containing all of the parts, you'll need to likely update this to the correct one. So subsection 3 is the model. This is where we'll generate the mesh, and we'll do that by right-clicking and editing it in ANSYS Mechanical. The next steps 4, 5, 6, and 7 can all be completed in ANSYS Mechanical, and that is what we will be doing actually. So as soon as that launches, we'll stay in there until we make it through the model, the setup, the solution, and the results. Okay, so as you can see, this is the same model that we created in SolidWorks, and to verify, you can open the geometry, expand it, select the specific part you're talking about. If you had multiple imported parts, you'll see each different solid body. And just to verify that we have our internal geometry, we'll turn the transparency down. You can see that this is the same solid body that we imported from SolidWorks. Next up, we need to make sure that the material assignment under the part is correct, and you'll notice that it's set to structural steel. Had we left this, the acoustics region physics region would not generate, so we'll change that to air, and that should be good for geometry. Materials, you'll just see what you had in your number 2 engineering data section. Coordinate system will be the default. And next we'll have to work on the mesh. So an important thing to consider with the mesh, if you have ANSYS Student Edition, which I do, is you're limited to less than 32,000 nodes or elements. Not the sum of the two, but individually, neither can exceed 32,000. So in our case, we'll need to change some of these element properties to give us a more coarse mesh. Otherwise, we'll run past our requirement too quickly due to this internal geometry, this relatively tight internal geometry specifically. So we will change the element order from program controlled to just linear, as well as we'll bump the resolution down, transitions fast, angle coarse, and actually we'll turn this to 1 just to show how to verify that your nodes are correct. So as soon as that generates, okay, so this is a really rough mesh, and it might not be accurate enough, but we did come in under our required 32,000. So let's bump this up to see what we can get away with. We're trying to get the closest number we can to get the best mesh. So we just surpassed 32,000. If we set up the analysis and ran it, we'd get an error saying there's a limitation in the product license we have. So we're going to have to bump the resolution down slightly. You could also set element size if you want. There's a bunch of different ways to tweak your mesh. But for our sake, we're just trying to get it under 32,000. And I mean, this should be plenty fine for our quick analysis we're doing. Okay, so now to recap, we have imported our geometry from SolidWorks. The material assignment has been set within it, and the mesh has been generated that also meets the product license requirements we have. So next we'll actually get to set up the analysis we're doing. So we'll start by running through the analysis settings. Here we need to set the range of frequencies which we're going to analyze over. For our case, we'll just call that 3000 hertz in intervals of 10 or 50. So every 50 hertz from 0 to 3000 we'll get a data point. Next, we'll need to set our acoustics region. So these are the physics regions within your body. If you had been doing a different type of analysis where you had a structural steel plate as well as your volume of air, you'll probably have a second physics region. By going to insert physics region, you would likely have a second structural physics region. In our case, we're only worrying about the air volume within the muffler. So we'll just verify that this is correct. You'll see that we have an acoustic region. And yep, these settings are all fine for our analysis, so we'll move on. Next up, we're going to need to insert the ports, the inlet and the outlet port. You can do this by right-clicking, insert, acoustics, port, and once you have that, we will be either selecting the input port and then apply, and next we need to choose the inside surface bodies. So essentially this port is the opening, and then all of these surfaces will count as the inside. And you'll notice it even highlights the front one, but when you apply, it deselects it, so it it knows to drop off your port surface had it already been selected. So we'll create a second port, and the reason we're doing a second port instead of multiple in the same command is that we wanted to say later in our solution we're going to do transmission loss between port 1 and port 2. So we want to have these as two different ports. So choose the port surface and apply. Next, choose the inside surface bodies and apply. So now we have our physics region set to acoustic for our solid model, which represents the air volume with inside our baffled and perforated muffler. We have the input port created, and we have the output port. Next, we're going to need to set our radiation boundaries. So we'll do that by right-clicking, insert, acoustics, radiation boundary. This one is okay to select both surfaces of the ports at the same time. And the reason we're choosing these surfaces is essentially these are the boundaries of our control volume. We only care about what is going on within this muffler. We don't care about these two surfaces as they open up outside of our control volume, essentially, because this side opens up to the rest of the exhaust system. So we have sectioned it there, and we're taking that same exhaust gas flow and putting it through. So we don't want anything reflecting off of this surface. The second side opens up to the atmosphere, so there'd be no logical reason why it should also be reflecting off this surface if it's just opening up into an essentially infinite body. This pretty much makes, radiation boundary pretty much makes these surfaces like a black body. Nothing will reflect off of them in your analysis. So now we have set up our physics region, the input port, the output port, and also confirmed that these are essentially removed from our analysis. That is another way to think about it. And our mesh is set up, so we need to set our input force. In that case, we're going to do a mass source, but if you right-click, insert acoustics, you'll notice you have a bunch of different options. You can do temperature, impedance sheet, static pressure, diffuse sound wave, incident sound waves, port in a duct. You could do a surface velocity, so if you knew the speed of the air entering your inlet pipe, you could choose the inlet face and specify, so many meters per second in what direction. But in our case, we're doing a mass source, and you choose the inlet port, apply, and we're going to set this value as 0.1029 kilograms per meter squared second. This is a value that we got from a research paper online. It was an empirical number for a high performance engine. You could really put anything there, but we wanted something that seemed somewhat realistic. And now that you have set up your geometry, your mesh, and then your actual solver setup, that would be your analysis range and increments, your physics region, your input port, your output port, confirming your radiation boundaries, and adding a source. You'll be able to solve this out. We'll talk about that primarily in our next portion of the video, but just for an idea, you can insert a bunch of different solution types. You can do transmission loss, and this is why we selected the ports as separate ones, is we want to be able to input port the first one, output port the second one. And once you have your solver ready, you can add in various solutions and run it. Down here you can see the progress bar. Once everything has ran, assuming no errors, it'll just say ready down here. If there's an error, you'll get a message down here, and you can double click that, and it'll take you to the messages section where you can view what was wrong, what tripped the error. In the next portion of our video, we will be talking in depth about the solution portion of ANSYS, what you can do with it, and what data you can get. Additionally, in the workbench, if you wanted to run a different type of analysis using the same geometry, you can click and drag and place your new analysis, and instead of having to re-import all of this geometry, you can simply choose your model if you want the mesh, or geometry if you only want the solid body. Click and drag. You can transfer it to where you need it. In our case, we'll transfer it right to the model of this modal acoustic analysis. And from here, you just follow the same steps. You'll work on your setup, your solution options, and then you can view the results once you run it.
So now that we have our model imported, our materials set, boundary conditions generated, and our mesh generated, we can go on to looking at the solved solutions and analyze the performance of our muffler. So in solution, you can add things that you want to look at, say pressure, total velocity, directional velocity, energy, frequency band. So you could do a frequency sweep using this option. Far field is basically doing analysis of a point and x distance away from your meshed elements. You can also use a boundary region that simulates an air boundary region, so that you can look at the effects away from the, say, the output or the outlet of the muffler. Then you can look at transmission loss, absorption coefficient, return loss, diffuse sound transmission loss. So here in my project, I've had the solution already generated and solved for. I have acoustic pressure, sound pressure level, transmission loss, absorption coefficient, and return loss. So here, let's just go into acoustic pressure. You can look at the pressure throughout the muffler, and you can see it animated throughout the frequency ranges from 0 to 1000. So what acoustic pressure is, it's essentially the dynamic pressure of your sound wave. It's a deviation of pressure from ambient atmospheric pressure. So essentially, your total pressure equals your static plus your dynamic pressure. And so you can see how that is affecting your muffler and what regions and how well it's attenuating the sound pressure throughout the chambers. So you can see that the primary chamber has much higher pressure, especially in the inlet port, and less so in the outlet port. And we can use this number to calculate the intensity if we also solve for the outlet velocity, which is I equals PV. So that intensity quantifies the amount of energy in the sound wave in units of watts per meter squared, which can then be converted to the logarithmic quantity decibels. And you can see throughout the frequency band range, it increases linearly pressure throughout your frequency band. So let's move on to sound pressure level. So this here is in units of decibels that I previously mentioned. So you can see here where essentially the sound intensity is highest throughout your muffler. So if you play your animation, you can see that the primary chamber attenuates a lot of the sound intensity. So you can see that it's pretty high here at the corner of the muffler in the first chamber, but once it gets to the second chamber, it's relatively much less sound intensity. So it is doing some work in reducing the sound intensity. Then we move on to transmission loss. So here you can see transmission loss graphed against frequency band range. So this is useful because you can use frequency to determine if your muffler is operating at the optimal frequency band range. So in a typical consumer vehicle, say it redlines at 6,000 RPM. So if you have a combustion cycle where you have one combustion per revolution, you'll have 100 hertz redline range of where your car is operating at. But most vehicles are, say, 4 cylinders, which typically means 2 combustion cycles per revolution. So that means 100 hertz times 2, and so you have a 200 hertz is where your limit of your operating range for a normal consumer car. So around 200 hertz, say at maximum we maybe have 10 decibels, right under 10 decibels of transmission loss. So for this muffler itself, it's telling me that it's not the most effective for its operating range. You can see in the higher frequencies, it seems to perform much better, say 40 decibels at 625. Just for reference, if you run a engine, say a motorcycle engine, six cylinder, or yes, a 4-cylinder engine at running at 12,000 RPM, which would be, so you'd have 200 hertz. With a 4-cylinder would be 400 hertz, so you'd only be operating here. So this muffler isn't exactly performing the best in our use case. It looks like you would probably want to see higher transmission loss numbers in the lower frequency range. So you would want to change some geometry, add some more baffling, things of that nature to improve the transmission loss throughout the muffler. So this graph is particularly useful for our analysis. Then you can look at absorption coefficient and how much your muffler is absorbing the sound waves. You could probably increase these by if you had, say, foam or some dampening material inside your muffler. Your absorption coefficient would probably increase, and your transmission loss would also increase along with it. You can see that your transmission loss follows somewhat inversely with your absorption coefficient. So the more you can absorb the energy in your sound wave, you can reduce the sound intensity and loudness of your muffler. And then you can also look here at return loss, which shows the power of the returning sound wave back to the inlet port. Uh, this is useful for, say, looking at your back pressure, back to your exhaust ports, and seeing how that correlates to your transmission loss. So with all these solutions, like I said, you can add more to analyze whatever parameters that you're looking for. You can change your input. Say if you didn't want it as a mass source, you can add, say, an incident wave source. If you know the waveform, say you put um, a pressure transducer inside, through your, or before your muffler, you can use that wave source and its magnitude and its frequency to have a realistic input through your muffler. You can also use surface velocity to, if you knew the velocity of your waves entering through the inlet. So these would determine how uh, these metrics change, and your geometry, of course, determines a huge portion of that. Like I said, you can also, to improve the design, you can add foam and have a porous material region with a porosity coefficient that you'd use. You could add additional baffling with multiple outlet ports with even more baffling to see if that helps your transmission loss in your frequency band range. You can use also different tube paths, different tube bends at the inlet outlets to further attenuate noise. And with this acoustic analysis, you can also optimize for Helmholtz resonance so that your sound waves propagate at the nominal frequency bands that would encourage and optimize the amount of engine breathing through your exhaust and essentially help you produce more power out of your engine. So that's basically it for looking at your solutions. Like I said, you can look at many different parameters that you'd want to solve for, and these are not the only limited ones, but transmission loss in our case is probably the most valuable graph that you would want out of this. And that's how you look at the results of an acoustic muffler analysis.